preparing compounds that primarily consist of carbon, oxygen, nitrogen, hydrogen. Those are sort of our main building blocks. And these are compounds that, in my group, our interest is really on molecules that have been isolated from some sort of natural source, has some interesting biological property, and that we think we could make it in the lab, and that might make us, enable us to make perhaps new compounds that might be interesting as medicines. So that's sort of the overall basis. But I'll show you what I mean by that more specifically. So what is a natural product? So this is really any molecule that's been isolated from a plant or bacteria or fungi. So for example, have you guys heard of salicylic acid? Yeah, so this is isolated from the willow bark, right? And then more commonly we know of a synthetic modification of salicylic acid, that's aspirin, right? So basically they add on this group here in red, and then we have a molecule that has some better properties in terms of being used as a pain reliever, right? So that's a pretty simple molecule. It's actually been known for, you know, a very long time, some of the medicinal properties. Penicillin, another common compound, this is another molecule, right? It's isolated from a natural source. It's actually produced by this mold. And the reason the mold produces it is that it's basically like, think about microbial warfare, right? Everyone wants to kill their enemies. So a mold wants to have an advantage over the bacteria, so it secretes some compound that's going to kill the bacteria so that it can thrive. And so you can imagine that if a mold has already evolved and already developed the tools to kill bacteria, that we should maybe sort of take advantage of that expertise. We hijack its molecule, we convert it into a medicine, and now we have antibiotics, right? So this structure here, this is how, as an organic chemist, we represent the structural entity that is that antibiotic, that natural product. And just to show you one more complicated structure, so same idea. So basically anywhere that you don't see an atom, that's a carbon. We have some implicit hydrogens here. There's a lot of information that's sort of encoded in that structure that you learn about once you become an organic chemist. But what I can tell you is that this is a much more complicated structure. Even you can look at it, you say, okay, with salicylic acid, there was one ring. Now we have, you know, several rings within the structure. It's more complex. This is a common chemotherapy. It's actually the sort of first line of treatment for many breast cancers. And this was also isolated from a natural source from a plant. Do you have a question?
Oh, have you memorized the periodic table?
Have I memorized the periodic table? I know the periodic table pretty well, but I don't actually know like all the molecular weights because, you know, you can see I have it on my wall. It's right there when I need it. But you know the trends. Actually, it's like anything that you're going to learn about over the course of your career. You figure out what things it's really important that you memorize every detail, and when do you need to know more holistically what the trends are and what the important information is that you should take away and sort of organize, because I think you guys are actually really smart, but I have limited bandwidth. I have to focus on the important things and take advantage of the, you know, information that we have on hand when you don't need to memorize it. But this is a really important compound. It's really molecules like this that we're interested in our group. In fact, if you look at the chalkboard, those are compounds that we're working on in our lab. And what we try to do is think about how do we actually build up these structures atom by atom in the laboratory? How do we develop new chemical reactions? So based on, say, known reactivity, extrapolating into, you know, making a hypothesis saying, oh, well, we know that this particular reaction works. Can we think about a new twist on that reaction based on my understanding of chemical reactivity? Maybe this will work. You test out the hypothesis, and it's very iterative. And so there's a lot of reasons why we like to make these compounds. And one is that, you know, nature's pretty good, but I'm sure if you guys are sort of listening to the news a little bit, you might have heard about, say, antibiotic resistance, right? So we might have a compound that starts off really good, but we're in this perpetual sort of battle to outsmart the bacteria, let's say. And so this is an example of a molecule, tetracycline. This was isolated from a natural source. Great frontline antibiotic when it was first isolated. But actually within just a decade of it being introduced, we started seeing resistant strains of bacteria to that compound. So one of the things that we can do as chemists is if we develop a way to make this molecule from scratch, from sort of inexpensive building blocks in the laboratory, we can tweak the structure a little bit and try and then rescue some of its activity against, say, a resistant strain. So for example, the chemist at Wyeth, this is a pharmaceutical company, they made just a few changes. You can see here I've highlighted purple. They basically got rid of these groups and they added the groups in blue. But really, in order to do that, they had to have some understanding of organic chemistry. And by making those changes, they now have a compound that's active against strains of bacteria that the original compound's resistant, or that are resistant to the original compound.
Oh, what are the lines on the...
So basically what we indicate here, like I said, so I'm not going to go into all the organic chemistry, but we're encoding information. So what this tells us is that here, whenever there's one line, that's what we call a single bond. If there's 2 lines, that's what we call a double bond. I don't have any here. If there are 3 lines, that's what we call triple bond. And it's because carbon can bond with other atoms in lots of different ways, right? And that affects the property, the strength of the bond, the geometry, the spatial orientation of the molecule. So for example, you know, we draw things very flat on that screen because it's sort of easy and simplified. But there is a 3-dimensionality to all of these molecules, right? So a carbon is what we call a tetrahedral center. And that confers this sort of spatial orientation. So this is not the molecule there, but you can see that that looks really flat. This has some 3-dimensionality, some depth to it. And so when we have, say, a hash like this, or a wedge like this, that's trying to tell us that something's coming out of the board or plane or going back into the plane. And so in order to shorthand things and keep things simple, because if you try and draw out everything the way it is here, it gets really complicated. So we sort of simplify it in this way. And there are other examples of why we might want to make natural products. Sometimes they're isolated from a source in a really low abundance. So this is a compound that's isolated from a marine bryozoa. It has really interesting anti-cancer activities, but we can't do clinical trials based on the natural source because it's so low in abundance. We'd have to harvest 14 tons of the natural bryozoa in order to get enough material to do 1 clinical trial. And I don't think it's really right for us to decimate an entire population and kill, hurt the ecology of the system just for advancing medicine. So that's where chemists can come in. We can actually design a synthesis where we actually make this exact compound in the lab, and then we can support the development of that compound as a drug.
Do you make it from scratch, or are there pieces that you then kind of glue together?
Well, so that's a very good question. So we get like catalogs that look like this of sort of our chemical building blocks that you can buy. And so part of it is, especially now in the information age, all of this stuff is searchable. So you can do a structure search and figure out what's a commercially available source. So we do have things like readily abundant, say, amino acids or sugars are really good sources. And then there's the petroleum industry. So we have lots of what we call small petrochemicals that are inexpensive that we can buy. But part of it is doing this analysis to take it back and say, okay, how much do I have to simplify it to get to something I can buy out of a catalog like this? And how expensive is that? And so there's a lot of different aspects that go into what we do. And part of what's coming about now is also computationally guided design. And so taking the information from an experimentalist like myself and collaborating with a theorist who now can actually use computers to do some modeling, predictions. We're in a very powerful age for chemical synthesis.
Can it do like 3D printing for a chemical?
You can do 3D printing for things like this, and actually people have used it for where you're trying to look at macromolecular assemblies, so larger like a protein. And if you're trying to fit together, how do multiple proteins, say, come together, you can sort of build out those pieces and have them to work with. But the chemical, not exactly, not yet. So basically what we want to do is discover, so our big picture goal is to make molecules like this, and we do that and then to study their biology. But in order to do that better than we could do it 10 years ago or 20 years ago or 30 years ago, our objective in our lab is actually to design and discover new chemical reactions. And this is probably the coolest thing about being a chemist, is that we can make things that have never existed before, right? I mean, we're not just studying existing phenomena, we're making brand new compounds, or you are learning, taking what we know about chemical reactivity and transposing it onto a new scenario, and then basically developing a new reaction. And so that's what we really get excited about, not just can we make the molecule, but can we think about new reactions that we can use in a specific context, but that someone else can use down the road. So that's where I'll leave it. I thought what I'd do, if you guys don't mind, because I don't want to take everyone through at the same time, because we had kind of a big group. So I'm going to grab a few